Hello, I'm J.D. Harrington, Public Affairs Officer for NASA's Science Mission Directorate. I'd like to welcome you to today's media conference where we will discuss the upcoming launch of NASA's newest space instrument, the Nuclear Spectroscopic Telescope Array, otherwise known as NuSTAR. Before we get started, though, a few housekeeping duties. We have 4 panelists joining us today. Each will give a short 3 to 5 minute presentation on their specific topic. Next, we will move to the question and answer session, taking questions from media here at NASA headquarters, questions from the centers, and others that are dialing into the telephone bridge. Questions can also be submitted to the panelists by the via the Twitter sphere by using the hashtag AskNASA. This panel media conference is limited to 1 hour. Today's panelists include Paul Hertz, NASA's Astrophysics Division Director at the agency's headquarters in Washington, D.C. Fiona Harrison, the NuSTAR Principal Investigator at the California Institute of Technology in Pasadena, California. Daniel Stern, the NuSTAR Project Scientist at NASA's Jet Propulsion Laboratory in Pasadena. And Yoonjin Kim, the NuSTAR Project Manager, also at JPL. And with that, let's get started. We open up with NASA's Astrophysics Division Director, Paul Hertz. Paul?
Thanks very much, JD. Well, we all know that NASA pursues space exploration. Not only exploration by sending humans into space, but also scientific exploration of our planet, our solar system, and the universe. NuSTAR does the last one, explores the universe. The data from NuSTAR and the science analysis that comes from it will help us understand how our universe came to be the way it is, how it got from the simple state of the Big Bang to the complex universe we see today, filled with galaxies, stars, planets, and even people. NASA puts telescopes in space because that's the only way we can do things that are impossible here on the surface of the Earth. Stars, nebulae, and black holes emit X-rays of the type that we use in medical X-rays, and these cannot be detected from the surface of the Earth. But the NuSTAR telescope will focus these X-rays onto its digital camera and send the pictures back to Earth for scientific analysis. From the point of view of astronomers, NuSTAR will be opening up a new window on the universe. And although we are going into this mission with many scientific questions that we know NuSTAR will provide the data that will give us the answers, like all of our NASA missions, we're going to find unexpected things out there that will lead us to questions and answers that we aren't even anticipating at this time. It's worth noting that NuSTAR was selected by the scientific community as a mission that's really important to do. Professor Fiona Harrison, the principal investigator, was one of several dozen scientists who submitted a proposal to NASA for a small astrophysics mission. NASA had these proposals reviewed by the peers in the scientific community, and they judged NuSTAR to have exceptional scientific merit and a really good plan for implementation, and that's why NASA selected it to be its next small astrophysics mission. This endorsement by the scientific community of the science that NuSTAR will do is one of the reasons I'm confident that we're all going to be really excited by the discoveries that come from this mission. So can I have the first graphic, please? Okay. Here are NASA's current astrophysics missions, including we've added NuSTAR on the left there. NuSTAR is going to be the 14th NASA astrophysics mission in operation doing science. Many of these missions are done with our partners, and I want to thank our international partners on NuSTAR at this time. NASA has partnered with the Danish Technical University Space Center and the Italian Space Agency to make NuSTAR a reality. The next speaker is Fiona Harrison, the principal investigator of the NuSTAR mission. Fiona?
Thanks, Paul. So as Paul said, NuSTAR will open a whole new window on the universe by being the very first telescope to focus high-energy X-rays. As such, it'll make images that are 10 times crisper and 100 times more sensitive than any telescope that is operated in this region of the spectrum. Now, I want to point out that NuSTAR operates at X-ray energies higher than what the sensitive telescopes like NASA's Chandra Observatory or ESA's XMM Newton can detect. Could I have the first graphic, please? So this image shows you what NuSTAR will look like after it's deployed on orbit. And I have to say, it's no ordinary looking telescope. What you see on the right are two high energy X-ray optics, which are mirrors which act like lenses to focus X-ray light onto digital cameras that are placed 10 meters away. So what you see on the left is where the two digital cameras are and the solar array from which we collect power. Now, believe it or not, NuSTAR launches on a compact Pegasus rocket from underneath the belly of an aircraft. And you may wonder, how can it do that and still be the length of a school bus? So the Tinker Toy-like structure in the middle that you see is what enables NuSTAR to do this. That ingenious mechanism, about a week after we get onto orbit, will unfold piece by piece to it over about 20 minutes to achieve this long necessary separation between the optics and the detectors. So NuSTAR is going to be a first in several ways. It'll be the first very sensitive high-energy X-ray telescope. It'll be the first ever to incorporate these novel X-ray optics and digital cameras. And it's also going to be the first astronomical telescope to use one of these extending focal benches in space. So together, this will enable NuSTAR to study some of the hottest, the densest, and most energetic phenomena in the universe, like, for example, black holes and the explosions of massive stars. Could I have the next graphic, please? So it used to be thought that black holes were rare and exotic. That was just 20 years ago. Today, we know that every massive galaxy like our Milky Way has a massive black hole at its heart. And if you can start the video for me, please. What this shows is what makes the regions around black holes glow brightly. So galaxies are full of dust and gas. This dust and gas is attracted by the gravity of the black hole. When it gets close, it organizes itself into a disk. And in this disk, friction heats up the material so that when it gets very close to the black hole, it's very hot. And the combination of this very hot material and particles that are accelerated close to the speed of light boosts emission into the high-energy X-ray band. So if you want to study the regions closest to the black holes, you'll use X-ray telescopes. Now, these regions, these innermost regions near the black hole, are only a few times the size of the event horizon. So in the event horizon, as you know, that's the region from which no light can ever escape. Material disappears, the black hole grows, and it's gone forever. But in these inner regions, gravity is extremely strong. And Einstein told us that light gets bent and severely distorted as it escapes from these regions. And by studying atoms in the X-ray band as they circle around before they disappear into the black hole, we can actually detect this strong gravity, the effects of this strong gravity. And we can, teaming with telescopes like Chandra and XMM Newton, we can tell things, for example, like how fast the black hole's spinning. Now, in addition, you'll notice there's beams of light headed out from the black hole. Well, those are actually called jets, and they're particles that are accelerated within a small fraction of the speed of light, and they carry so much energy in that in some cases they can affect the entire galaxy. And teaming with NASA's Fermi Gamma Ray Telescope, NuSTAR can study these jets, these regions of accelerated particles, and try to understand what creates them. Could I have the next graphic, please? So if you were stargazing and you had eyes that worked in the high-energy X-ray band, and you looked up in the sky, not in the plane of the galaxy, but up in the extragalactic sky, you would see the glow of many hundreds of massive black holes scattered throughout the universe. And this image, what this shows you, is what that glow looks like with the current best telescopes that we have. We can't resolve it into sources. But if you can give me the next graphic, this is a simulation of what NuSTAR will see when it surveys regions of the extragalactic sky. It'll be able to resolve this glow that we know most of the energy in this glow in the X-ray band comes out in the NuSTAR window. It will be able to resolve this into sources, which we can then take other telescopes like Hubble and Spitzer and look at the galaxies that these black holes reside in and try to understand how the black holes are affecting the growth of galaxies over the age of the universe. So if I could have the next graphic, please. So this shows you one of the key NuSTAR technologies, which has been developed, I should say, by NASA over the last 15 years by my team, funded by research and analysis programs and the Balloon program. We were able to develop these very novel optics. Now, it doesn't look anything, of course, like an optical telescope. Optical light, unlike X-rays, it will reflect off a mirror at any angle, whereas X-rays only reflect at very glancing angles. That means the reflectors or the mirrors have to be placed almost parallel to the incoming X-ray beam. And so to intercept a lot of X-rays, what we have to do is nest hundreds of shells inside one another, like Russian dolls, so that we can intercept a large fraction of the X-rays coming into the telescope. So NuSTAR has, in fact, 133 of these shells. Not only that, we have to coat these shells with special reflective coatings that consist of hundreds of layers of thin films. They're kind of like the anti-reflective coatings on your glasses, but they work to enforce the reflection. And these films are only a few atoms thick. Okay, and there's hundreds of them on each surface. But by doing this, we're able to extend up to significantly higher energies the X-rays that we can focus. So with that, I'd like to have Dan Stern, the NuSTAR project scientist, tell us a little bit more about the NuSTAR science program.
Thank you, Fiona. If our eyes could see X-rays, our galaxy would be lit up with black holes, neutron stars, and supernovae. I'm going to talk about a range of science investigations that NuSTAR will undertake within our own galaxy, so much closer than those supermassive black holes billions of light years away that Fiona spoke about. We have a range of programs within our galaxy. One is our galaxy, like all massive galaxies, has a supermassive black hole at its center. Ours is called Sagittarius A star and weighs about 4 million times as much as the sun. And sometime in the early fall, we'll take part in some coordinated campaigns with telescopes all over the planet and in space, watching the black hole in the center of our galaxy. We'll work with Chandra at the lower energy X-rays and NASA's Fermi telescope at higher energies, and some very large telescopes in Hawaii, Chile, New Mexico. And we'll watch the flickering of the black hole in the center of our galaxy and watch it as it feeds and learn both how black holes grow and what the environment around the black hole is. Another key part of the NuSTAR science program is studying supernova explosions within our galaxy and the local universe. Supernovae are very energetic events. The most massive stars in the galaxy burn their fuel quickly, and then when they've used up all their fuel, they become unstable. And so the mass and the gravity is pushing inward, and they no longer have pressure pushing out from the fusion and the energy production. So the star actually collapses, bounces back, and has a big explosion. Could I start my first graphic, please? So this shows a simulation of a star. It runs out of fuel, it collapses, and then it explodes, spitting out material that used to be within the star into the cosmos. One of the most amazing results from astronomy is that we are all star stuff. The carbon in our bodies, the silicon in our computers, the gold, silver, platinum in our jewelry, all of that was formed within stars. And it's these huge cosmic explosions like supernovae that spit that out into the cosmos. These remnants explode out at thousands of miles per second. And much like a bomb squad might look at the remnants of an explosion and try to understand how that explosion happened, NuSTAR scientists will look at these remnants from supernovae and try and build back the physics of the explosion, which are not so well understood currently. NuSTAR will look at some supernova remnants that went off in our galaxy historically over the past few hundred years. Typically, a galaxy like the Milky Way has a supernova go off every 30 years or so. It's been about 100 years since we know one went off in our galaxy. So we're really crossing our fingers that over the next couple of years, while NuSTAR is up in orbit, a new supernova will go off in our galaxy, and we'll slew over as fast as we can within about 24 hours and start studying this explosion from the earliest stages. Another part of the NuSTAR program is to study the remnants of the explosion. So the very core of the star is left behind. Very large stars leave behind a black hole. Slightly smaller stars will leave behind a neutron star, which is essentially just a huge nucleus of an atom weighing as much as the sun and the size of Manhattan. These are very exotic, very extreme sources, very strong magnetic fields. And NuSTAR will study the high energy emission from them and get a better understanding of the physics of these exotic objects. Finally, NuSTAR will also do some observations within our own solar system. Can you bring up the next slide, please? So here's a picture of the sun. NuSTAR has a range of programs studying the sun. We'll spend about 2 weeks of our 2-year baseline mission studying the sun. We'll study very large flares, also called coronal mass ejections, that happen sporadically across the surface of the sun. And then we'll also study small flares and microflares and nanoflares on the surface of the sun. The sun is surrounded by this corona or atmosphere of million-degree gas, which we don't really understand how it maintains that temperature, how it forms. One of the dominant theories explaining it is nanoflares, but no telescope prior to NuSTAR has had the sensitivity to see whether nanoflares actually exist. So in a few hours of observations, NuSTAR will answer this long-standing question that solar physicists have been scratching their heads about for years. The NuSTAR science team consists of about 100 people around the planet, and we're all eagerly awaiting the launch in about 2 weeks from now, and then our first science data about a month after that. NuSTAR will be the first mission focusing this high energy light, and much like Galileo 400 years ago was the first one to focus optical light or visible light, NuSTAR will be the first mission to focus these high energy X-rays, and we expect amazing discoveries from it. I'll next turn the speaker over to Yoonjun Kim, the project manager from NuSTAR, who's also at JPL, and he'll talk about what to expect over the next couple of weeks.
Thank you, Dan. So let me start with the current NuSTAR status. So as Fiona explained, there is a optics and then spacecraft, and that is connected by 10-meter mast. That is a configuration in space. So on the ground, the mast is stowed. So next graphics, please. As you can see that the mast is stowed, you can see the top, there's optics, and the bottom that you can see is the spacecraft. So when it's all stowed, the height of the spacecraft is approximately 2 meters, just shorter than the height of Karim Abdul-Jabbar. And that spacecraft, compared with the launch vehicle, is tiny. So right now, the NuSTAR spacecraft is integrated with the Pegasus launch vehicle at Vandenberg Air Force Base in California. So the next step is to take the Pegasus launch vehicle with the NuSTAR in it, will be integrated with the L-1011 airplane. So on June 2nd, this coming Saturday, the Pegasus will be installed underneath the L-1011 airplane. On June 5th, L-1011 will take off from Vandenberg Air Force Base, and NuSTAR arrives at Kwajalein on June 6th. The current launch date is June 13th with the 2 backup days, 14th and 15th. And the reason that NuSTAR launches from Kwajalein is very close to the equator. So if it is here is Earth, the NuSTAR will rotate around the equator to avoid the interference from charged particle that is trapped by Earth's magnetic field. So let me describe to you what happens on launch date. So very early in the morning, Kwajalein time, L-1011 will take off. So remember that under the L-1011, we have a Pegasus launch vehicle. Inside, we have a NuSTAR spacecraft. So when L-1011 gets to the drop point, it actually drops the Pegasus, the launch vehicle, about 5 seconds until the first stage ignition happens. The Pegasus is a 3-stage rocket. That means that there are 3 ignitions before NuSTAR reaches the desired orbit in approximately 800 seconds. So the movie, please. So L-1011 at 41,000 feet and 5-second drop with the autopilot on. First ignition. And second stage ignition. Then we have a fairing separation and final ignition. Can you stop the video, please? Thank you. So at this point, NuSTAR is separated from Pegasus launch vehicle. So the first thing that NuSTAR will do is to contact ground station saying that I'm here, I'm ready to operate. And then, as Fiona mentioned, the blue color that's showing in the picture is a solar array. So solar array is automatically deployed to charge the spacecraft battery. And then we start what we call the spacecraft checkout. So during the spacecraft checkout period, we check out all the spacecraft components to make sure they are working. In about 1 week after launch, we deploy the Mast. And as Fiona described, that the optics and detector requires about 10 meter separation. We accomplish by deploying the Mast. So let's deploy the Mast. Restart the video, please. So as you can see, later when it deploys, there's some segment comes out, what we call the bay, and each segment comes out and locks. So each segment comes out locks. There are 56 bays to be coming out and locked to fully extend the Mast. So this Mast technology was originally developed for International Space Station. It was also used for space shuttle mission, SRTM, Shuttle Radar Topographic Mission, in 2000. The NuSTAR is the first space telescope that utilized this technology. So now, after Mast is deployed, the optics and detector is at the right location to make a high-resolution X-ray image. So we can start the instrument calibration, which lasts approximately 3 weeks. So after instrument calibration is completed, NuSTAR is ready to listen to what X-ray universe has to tell us. Back to you, JD.
Thanks, Eugene. And with that, we'll get started with the question and answer session, because we have quite a few people that are joining us today from a variety of locations. Reporters will be limited to 1 question and 1 follow-up. If time permits, we'll go around and ask a second set of questions. We'll start with the beginning, and if you would, identify yourself and your media affiliation, and if possible, target your question to a specific panelist to avoid any confusion. For those who would like to ask a question on the phone bridge, push the *1 keys on your telephone to be placed in the queue. And once again, to use Twitter, send your questions to #AskNASA. And with that, let's begin. I believe we have 1 question here via the Twitter sphere already from G. Dunn PT. He asks, is there a black hole at the center of every galaxy? And if not, what is allowing every star to maintain an orbit around its center?
Sure, I can take that question. Well, as far as we can tell, there is a massive black hole at the center of every massive galaxy, so galaxies that are like the Milky Way. The very smallest galaxies, it's still a bit a matter of debate. But as it turns out, the mass of the black hole is only about 1/1000th times the mass of all the stars in the galaxy. So it's really the gravitation of all the stars that bind the galaxy together and make the stars orbit the galaxy.
Okay, we're going now to the telephone bridge with Space.com's Dennis Chow.
Hi, thanks for taking my question. I think this is for Fiona. I was just wondering if the delay earlier from the original launch date, if that had any impact to science or the cost of the mission?
Okay, I can take that. So let me just say that we've been developing NuSTAR for 5 or 6 years now, building the mission, and the delay was a few months. So from my perspective, it's been a career, and a few months is not a big deal. From the science perspective, it really didn't affect much. We've chosen slightly different calibration targets, but the science program is unchanged. And I think I'll let Paul Hertz take the question about the cost.
Thanks. Yes, there obviously is a little bit of increased cost to keep the pre-launch team together as we're moving towards the launch date. And so the launch delay raised the cost of the mission by several $1 million out of the 120-something total cost to date.
Right, 165 life cycle cost.
Okay, so it's a few percent.
Okay, we're going back to the telephone bridge now with Dan Leone from Space News.
Hi, everybody. Thanks for throwing this together. Could you confirm the final development cost once more? And then my original question is, when are you going to be up for an extended mission review?
NuSTAR will be eligible to participate in the 2014 senior review, at which time we'll make a decision as to whether to extend their mission into 2015.
Thank you, Paul. We're now going back to the telephone bridge with the Aviation Week's Mike Mitchum. Hello, Mike, you with us? All right.
Hello?
We have another Twitter question here. Where is the data going to be stored, and is it going to be available to the general public?
Yeah, I can take that question. So the data comes down to a ground station in Malindi, Kenya, that's operated by the Italian Space Agency. From there, it gets sent to our Mission Operations Center at UC Berkeley, and then goes on to the Science Center at Caltech. After we validate the data and make sure that it's all there and all right, then we send it to a permanent archive at NASA Goddard Space Flight Center, and that archive will make the data available to astronomers around the world. Well, actually to anyone around the world.
All right, we're going to go back to the telephone bridge now with the Register's Ian Thompson.
Hello, thanks for taking the question. I'd just like some more details on the Mast technology that was used to separate the telescope from its rocket stage. It said it was developed on the ISS and also on the Space Shuttle mission. Could you give some more details, please?
I can take that, but I didn't hear the question very clearly. So anybody can repeat that question for me?
Oh, I'm sorry. I was after more detail of the development work on the Mast that was apparently carried out on the ISS and also for the Space Shuttle mission.
Yes, I can take that question. As you saw, that the Mast has a lot of component in there. It was developed by ATK Goleta. First, the ISS, International Space Station, mast is 30 meters. The SRTM, Shuttle Radar Topograph Mission mast, was a scaled version of that actually was 60 meters. It's the same company built it, and what we did is we took the design of a SRTM mast, which is 60 meters, and scaled down to 10 meters. So we built it very early, a prototype. Actually, it's a proto-flight, but we built it first and did a deployment test. And we did a lot of testing, and thermal cycling and testing and vibration tests for the mast. So we're confident that the mast will work nicely. In fact, the ground is actually the worst place to deploy this mast because of gravity. So we built this, what we call the gravity offloader, to do a many deployment tests. I think we are over 20 times we deployed the mast, fully deployed the mast. And then we did a vibration and then deployed it again before it actually installed on spacecraft. So that's the development cycle. And currently, we want to make sure that Mast is actually working after we deliver the spacecraft. We did the first motion test, so several motion. One or two bay has been deployed. So that's the kind of the development work that we did for the mast of NuSTAR.
Thanks, Yunjin. We're now going back to the telephone bridge with Aerotech News' Raphael Jaffe.
Yes, This is a question for Dan Stern and perhaps Dr. Hertz. There has been, I'm sorry, are you hearing me?
Yes.
Okay. NASA science missions have had miserable luck with shrouds not separating. Is there such a shroud involved in NuSTAR, and how do you feel about it?
I'll take that question. So yes, the Pegasus rocket does have a shroud, and the Pegasus design has been studied very carefully by both the manufacturer, Orbital Sciences, and NASA. It's been tested extensively, and we're all very confident that the shroud will deploy correctly.
Thanks, Paul. We have a Twitter question here from, oh my God, Whatabee. It is specifically to Paul. Will NuSTAR be used in conjunction with SETI?
Well, that's an interesting question. To the best of my knowledge as a scientist, we have no expectations that if there were intelligent life elsewhere in the galaxy or in the universe, that they would be sending out signals at the wavelengths that NuSTAR will be sensitive at. So there's no expectation that it would be useful in that particular scientific search.
Thanks, Paul. We have one more on the Twitter line from One Little Becca. As a follow-up to our data question, we asked, will the data be fairly easy to interpret?
Well, in some ways, I have to say we hope not, because that means we're finding unexpected, unusual things. But if you're just asking the straightforward question, is it very complicated to make an image? No, it's fairly straightforward to make an image and to make a picture with NuSTAR. We have to just place the individual X-rays that we detect place them onto the sky, back project them. And that's a fairly straightforward process. We have all the software ready to go. So we'll have our first light images available from NuSTAR very shortly after we take them.
And if anybody goes to the NuSTAR website or the archive website, they can download those images themselves. Is that correct?
That's absolutely right.
Great. We now go back to the telephone bridge with Space News' Dan Leone.
Could I get somebody to repeat a little bit puzzled line earlier?
Hey, Dan, if we could get you to repeat the question, please.
I'm here. Would somebody please repeat the final development cost? It was unclear on the phone earlier because of interference on the line.
Go ahead.
Yunjin, you...
The life cycle cost is at the end is approximately $170 million.
Don't say that. What that includes?
Oh, that $170 million includes the project development, as you can see, the spacecraft and instrument, and all other system engineering and management, and the science operations, and it includes the launch vehicle as well as the program office oversight cost.
All right, appreciate that. We've got a question here from Shantix, who's saying, can NuSTAR see the event horizon? If not, how close to it can it see?
Okay, I can take that question. We actually can't see all the way to the event horizon, because what happens is that when you get very close to the event horizon, matter no longer circulates around the black hole. It starts to fall in very rapidly, which makes it hard to see. But the area we can see is only about 3 times the size of the event horizon itself, so it's still very close in.
All right, one more Twitter question here. I believe NuSTAR is an Explorers program mission. Can you explain what Explorers is and how it comes about?
Okay, I'll take that question. The Explorers program is actually NASA's oldest program. Explorer 1 was NASA's first successful satellite launched. The Explorers program issues calls for proposals to the science and engineering community and for building scientifically meritorious small missions. And NASA reviews those proposals and selects the very best one, and that's what we fund. NuSTAR was submitted in what year?
2003. Yeah.
So we think around 2003, and was selected and developed over the years. We're also developing. We have other missions that have been launched in the Explorer series and are still operating in space include the SWIFT mission, which is up there now, and the Explorer program will be launching a solar telescope called IRIS early next year.
All right, thanks, Paul. And that's going to do it for today's NuSTAR 1114 or L14 briefing. I'd like to thank our panelists for joining us today. I'm sure you look forward, as we do, to a successful launch coming on June 13th. And to find out more about the NuSTAR mission or any of NASA's projects, you can visit us on the web at www.nasa.gov or along any of our social media projects such as Facebook, Twitter, Google+, YouTube, and many others. Until next time, have a great day. Thanks.